Hello class. Today we are going to learn more about valence electrons, atoms, and how they bond into molecules and compounds. Now, you might have seen in the past little models that do things like this and look a little bit like chemistry in your mind, right? Well, I'm going to talk to you about these models and how they work and how they help us visualize how atoms hook together. Now, they aren't really functionally what an atom really does. We just talked about that last week and how we have orbitals and things going here and there and everything. But this can help us to understand which things are going to bond with which things, which is what we're really trying to figure out right now. We have these bare atoms and they want to join together with other atoms to make stable compounds. In other words, they want to be happy in the place where they are and stay like they are. So we've talked about a little bit what how many electrons an atom wants. And we talked about how they really like to have 8 in their outside valence electrons. So they get out up here and it's big and it kind of gets a little more messy down here in this lower region. But if you're looking at the periodic table, except for hydrogen, which wants 2, and helium, everything else along here really wants to complete 8 atoms in its outer valence shell. And so valence meaning the outer ones. Everything inside, remember, is shielded and a little bit protected. So the outer, we're going to try and complete 8. So if I use a little model like I was showing you before, you can buy like a whole kit that has a bunch of these beads in it. And what it does is it does something like this. It says this one's going to be hydrogen, and you can't really see very well, but there's like one hole in a hydrogen. And what that means is hydrogen has one electron. It'd really like to have another one. So that's sort of one bonding location. You could think of it like that. And so we can take a little piece and we can stick it in there and say, this hydrogen really wants to stick to something. Okay, well, what if I take another one and I'm going to say this one's an oxygen and it has, hard to see, 2 bonding locations. Now, why is that? Well, if we look at oxygen on our periodic table, it's over here and in group 16, which means that it has 6 valence electrons, it would really like 2 more. So we're not really differentiating between hydrogen, which is lacking 1, and oxygen. Well, I guess it's really like kind of lacking 2, huh? So anyway, it wants 2 more connections. It would really like to have 2 more electrons. And so what we can do is say, well, hey, what if we hook hydrogen to an oxygen? That would make them both happy in one way. They both have 1 connection. Hydrogen's good, but what about the oxygen? It still has this empty hole. Well, if we fill that hole, we could like maybe stick another hydrogen in there. And now what do we have? We have a molecule. 2 H's, 1 oxygen, that's H2O. We have water. And so we can see that both atoms are happy because they have all of their little spots filled, and this makes water. So we can do this with other atoms. Like, let's look at carbon. Carbon right here is the foundation of all life because it can form so many different things. Carbon has 4 atoms in its valence shell, and so really, or 4, excuse me, 4 electrons in its valence shell. So it would really like to have 4 connections in it. Now, there are other ways that carbon acts, and sometimes it's only 3 and sometimes it's 2, but we're going to talk about the most common, which is 4. So we can form things like methane. Methane is CH4, so carbon and 4 hydrogens. You can see that all the 4 missing spots on the carbon are filled, and hydrogen is happy because each one of it is sharing a bond with the carbon, right? So we have a nice little methane atom, a model of a methane molecule. Let me get this right. Okay, how about, I don't know, let's try and build one called ethene or ethylene, depending on if you're the scientific or the common name of it. Now, ethylene is C2H4. So you can see here that H4 filled 2 spots on each of these carbons. But then there were 2 spots left on the carbon. And so if we had only had 1 bond, like you might have thought, if we just bonded the carbons together, there are these 2 missing spots that really want something. And so what carbon did in this case is formed what we call a double bond. It bonded or shared doubly, shared its electrons twice, and we call that a double bond. Okay, so this one is ethylene. Okay, what about one? There's one called ethane, which is C2H6. That one might be a little easier. I'm just going to take a carbon and I'm going to start sticking hydrogens on it. We've got 6 of these, so I could stick 4 on here, but then there'd be nowhere left to connect it to the other ones. So what if we just connect 3 of them on this first carbon? And maybe I'll take the second carbon and I'll connect 3 more hydrogen. So we can now say C2H6. I've got H6 and I've got 2 carbons. How many bonding spots do I have left? Well, I have 2, 1 on each one. So they could just hook together. So I can take 1 bond and fit it into each of those. And so you can see everything's filled. So if I do ethane instead of ethene or ethylene, you can see that because there was a different number of hydrogens trying to bond, it formed a single bond instead of a double bond. All right. So again, these are just models. Now, I'll just show you a really fun one. What do you think this one is? Well, it took me a while to build this one, but this is caffeine. This is a model of the caffeine molecule. Caffeine is, let's see, C8H10N4O2. And you can see that there are several double bonds between carbons. In this one, there's a double bond between a carbon and this blue is nitrogen, and the red ones are oxygen. So you can see this model of caffeine. So this little kit helps kind of model how things stick together. What about another common one? You might notice I didn't do anything here with, like, say, sodium chloride. I've got sodium over here and I've got chlorine over here. Can I model those? Well, if I look in my little kit, it has a little paper and it says, well, let's see. You have a chlorine in here and it is green. So I'm going to grab a green chlorine and look at that. Green only has 1 bonding place. So I know chlorine, that's because it's in this column right here. And it only wants 1 more electron to be full. And we happen to know that sodium over here, we've talked about how table salt, sodium chloride, it bonds together because sodium has 1 extra electron. Well, you know, my kit doesn't come with any sodium. Why do you think that is? It's because it's a different kind of bond. So the kinds of bonds we're talking about here, we call these covalent bonds. That means, remember the valence electrons, covalent meaning this valence electron and that valence electron, meaning they're together. So it's not really that this 1 electron is like zooming between this atom and this atom, or even what we used to think, which was that they were just attracting each other together. The truth is, remember how really the electrons are sort of a cloud in some shape around these 2 nuclei? So you bring these 2 together and really their clouds are overlapping. So this electron is shared between both nuclei because the clouds where those electrons might be are overlapping. We call that a covalent bond, as in the valence electrons are being shared. Now, covalent bonds happen mostly between nonmetals, so all the different nonmetals together. But there's a different kind of bond, the kind we have for table salt, where you join a metal with a nonmetal. So one of the metals from over here with a nonmetal from over here, we're going to call that an ionic bond. And that's because, for example, chlorine wants another electron, and so maybe we'll stick it on here. I'm going to call this an electron. So chlorine gains an electron, and let's just pretend we have this, I don't know, we'll call this one sodium, okay? Sodium gave up an electron, and the 2 of them are then, one has an extra electron, one has 1 too few electrons, and because of that, they both have a different electronic charge, and they're drawn together. And so that bond is called an ionic bond because each of them is an ion, and those ions are drawn together, so it makes an ionic bond. And so that's sort of a different bond than a covalent bond. What about all this blue stuff in the middle? Well, metals form all kinds of bonds, but really if you get a whole bunch of metals together, we call that a metallic bond. And you'll learn more about metallic bonds next week, but a metallic bond means that a whole ton of these electrons are shared. And that's why metals behave as they do. That's why they transfer heat well. That's why they transfer electricity well, is because it's almost like you have a soup of electrons around all the nuclei that line up nicely. And those electrons can travel easily because they can go from 1 to 1 to 1 of each of these atoms, and you can move electrons and move electricity. So you have these different types of bonds. All of this stuff is just to help us visualize it. It's not really exactly what's going on. There's one more way we have to visualize things, and we call that a Lewis dot diagram. And this is the way we're going to write it down. So we can just write the symbol of an element. Say we write down chlorine, or we write down hydrogen, or we write down helium. Then we're just going to put the number of dots in the valence shell around that. And so we draw these dots in what we call a Lewis dot diagram. And a Lewis dot diagram helps us decide what is going on in an atom. Although this isn't reality, Lewis dot diagrams don't really represent an atom. These models don't represent an atom, but they are super helpful in finding out for us or modeling to us which things are going to bond with which things. And that's really what we want to figure out now, is how things bond. Wow, I almost forgot to teach you one really important thing, and that's about the difference between a molecule and a compound. Okay, we did some things like this and showed how different elements can bond together to form a, what do you think this is? Well, it's a compound. Compound meaning more than one thing stuck together. But you also know that, for example, hydrogen doesn't usually hang around by itself. What it really does is it's got this empty hole and it'll just bond to itself. And it'll form H2. And we've got this like H2 floating around, right? Or how about oxygen? Oxygen with its two bonds, well, it likes to bond with itself too if it's just sitting around. And so we might form something called O2. What do you think about that? So we've got O2, we've got H2, we've got this one, which we said is methane. So are these all molecules? Are they all compounds? They are all molecules, meaning that they are atoms chemically bonded together. Sorry about dropping that one. But they are not all compounds. This one is a compound because it has more than one type of element bonded together. Caffeine, definitely a compound. But O2, H2, these are molecules because there's more than one atom bonded together, but they are not compounds because they are all the same type. All right? Compounds, molecules. All right, thanks for learning with me today. I hope that you understand more about how models can help you understand bonds and the difference between the different sorts of bonds. And you'll have fun trying to predict which things are going to bond together this week. Thanks.